This is a topic near and dear to me because, and this may irritate some people, but most of the guidelines that we have for development of said basins and said traps are incorrect. Not because of the fact that the numbers are incorrect, it's how we're looking at it. And that's what I'm going to do in here. So you're going to see a little bit more of the technical end of stuff on here. Try not to go to sleep. We'll leave all the calculus out of it for you, so you won't have to do that. But let's start talking a little bit about this. How are sediments in runoff waters captured? That's our topic here. I don't care about erosion. Well, I do. Erosion control, yes, that's a whole topic by itself. When we put a barrier in front of an inlet, we're trying to remove sediment out of runoff water. And that is one of the most difficult things in the world. And nobody in this room, nobody in Hawaii, nobody in the United States can ever stop all the sediment from leaving a site. It cannot be done. But boy, we can make a major improvement on reducing it. And that's what I want to talk about. There's two techniques that usually people use. It's barriers and filtrations. Filtration I'm going to leave out because not many of you use filtration. And besides, when that phone goes off, when indeed you have filtration, they'll eventually clog up and you're going to have a barrier. So I'm going to concentrate on barriers themselves. And of all the structures that you put on a construction site, there's only one that is truly effective in reducing sediment out of runoff waters. I'm not talking about erosion control, I'm talking about sediment control. And that is a properly designed pond. They come in shapes, different shapes and sizes. This is great for subdivisions. This was a highway project we worked on. And this works good, this works good. It depends on the size of the basin that's contributing to the pond, whatever. Then you have the small ones, such as what you see into here. So it varies. But they all have the same principle of how they work. Or more importantly, how they do not work. And we're going to cover that as we go through it. By the way, let me go back. This is what I'd like to see, and we're going to talk about that in a few minutes. But usually I go out to construction sites and get called in to provide some expertise on it. I often get something that looks like this. And you may think that is a terrifically good sed basin. It is a lousy sed basin. And the reason for it is that the design parameters weren't thought of. They were interested in how to get the water into a pond and how to get it out of the pond. They could care less at this time how to remove the sediment. And remember, sediment itself is only about 5 to 10% of the total amount of water coming to the pond, depending on how steep your slopes are. This particular case, there's a shape all the way around. It's almost like a square shape in the case in there. And right into here was a bunch of sediment, and here's the infamous Eddie bales that he loves it all the time, which by the way, Eddie, thank you for saying you don't use bales. You don't have to worry about it in Hawaii. This looks good, fantastic. Look at the sediment I caught. But the one thing we forgot about, it rains. This was in Florida, by the way. It rains in Florida just like it does in Hawaii. And when it rains, fills up the pond, it goes right into the inlet. And this is what we found on the downstream side of that inlet. All of that. This was stamped by an engineer plan that just really didn't quite have the knowledge that they should have in designing these. And remember, contractors are going to install that. We as designers, if we have designers in the room, I hope we do, or the regulatory people who approve it, they're going to install exactly what's on the paper. So let's make sure we do that, get that paper done correctly. An efficient pond, this is just a typical detail to go with, needs to accommodate flood flows coming into it. There's the first word right there. Do not worry about just the containment volume. Worry about how much water's coming through our system. That's the first priority. Because it's got to go out eventually. We got to have contained water. We got to control the discharge of what's in the contained water. If it has a lot of clays, we have to go 48 or maybe 96 hours to drain it, not 12 hours. And if we have discharges in there, remember we've got to have design outflows. This and this are going to be the same for our design parameter to begin with. And our whole goal is to capture large particles and as many little particles as we can get. And you will never, that I'm aware of, have immediately pure, clean water without using some chemical treatment like a flocculant. It ain't going to happen. So with that in mind, let's take a look at this. Traditionally, our criteria we have is saying, let's fill up a bucket with water. So we take that bucket and we fill up that bucket with water, and we this magic number down here, 3,600 cubic feet per acre, which is what Hawaii uses, which is what most of the nation uses. And most of the nation's not correct on that number, by the way. You'll see that coming up. So we get that in there, we let it sit for a while, we start taking water off, and if you take it off with a riser pipe at the bottom of the pond, you're taking all the sediment that's accumulated in there, and then you've just made it go to zero. You're supposed to take it from the top. Think about it. Where does the least amount of sediment is going to be? It's up here. Is it clean water? No, not unless you do some treatment. This is just a real quick graph of showing what happens with particles. For a particle to fall a 4/10 of an inch in water at 32 degrees Fahrenheit, and yes, water is a liquid or an ice at that temperature. You can't read it in the back, but that says 5.7 hours to fall 0.4 inches. Make that particle is about a 0.001 millimeter, pretty doggone small, clay colloidals. Increase it by a factor of 10, it goes from hours to minutes. Increase it by another factor of 10 to get sands, it's down now to seconds. Most of the times I see in ponds, they're down in this category, getting rid of the sands, which is good, nothing wrong with that. But the damage is going to be up in this category over here. And that is a tough one to take care of, very tough. So, instead of thinking about a bucket, I want you to throw that bucket concept out of the window. And now start thinking, not the bucket, and like we have in this one here, but instead think about a bathtub. Bathtub, water comes in on this end, goes to that end. Water comes on this end, goes out that end. Why? Because it's a long flow path. Every pond should be long, not square or circular. If you have a square or circular pond for said pond on your site, you have probably a very ineffective, unless you've either put baffles in or whatever cases may be. Because you want that water to take a long time so that the particles can settle out. Question is, how long is long? Or how short is short? So we think about this, and the traditional method of this is that we have a certain volume that we're going to capture, and we will just ignore the flood flows. I'm saying this thing differently. Let's start with the flood flows and then end up with the minimum volume to treat. But, you'll see why in a minute here. So that one I'm going to tell you, ignore it. Even though you have in your criteria, capture 3,600 cubic feet per acre. Throw it out for right now. But don't throw it too far away because we'll have to come back to it. And we want to talk about the design discharge. Every civil engineer who does a plan for drainage is going to calculate what's going to be the historic flows or the base flows, 100-year, 2-year, 24-hour storm events, and so forth. That's part of our criteria. Use that and start with it and think about the bathtub concept where water is already discharging out. What can I do to make sure I minimize this damage and end up with a controlled amount of sediment that I can treat with my sed pond. Different little concept. So that's the one that we're aiming for. I'm just going to give you these little things, and by the way, this is probably about 2 to 3 hours worth of sessions of talking if we got into real minute detail with all the math and everything in there. So I'm just giving you enough to do it here. The thing that's important, the higher the water leaves our structure, the lower the effectiveness is of capturing any sediments, except maybe rocks, sands. But as soon as we stop having the flood discharge occurring on here, everything changes. So that if we have just a slow discharge leaving our site, then we can start capturing all the small particles that we're looking for. And that's the concept that you're going to see a little inkling of. It takes a little bit more to go through in reality here. So I'm going to be using what I classify as the bathtub concept. And basically, the first thing I do with my bathtub concept is, if you notice the shape, long and narrow shape, I have a design outflow. That's my beginnings. And that design outflow has got to be equal to the design inflow. So in other words, the bathtub is full. Water comes in, water goes out. Comes in with 10 CFS here, it's going to leave 10 CFS there. That's the worst case scenario. But then, within my bathtub, I have a place that the water's all going to be mixing up. So that's what we call a turbulent flow zone. Then I have another part where it's going to start accelerating. So there might be some particles down on the ground in here, but it's going to be trying to go over the spillway or through whatever mechanism we have. It's going to maybe start picking up some particles. But there's only one area that indeed is going to be relatively calm in this long bathtub, and that's the laminar flow section. So that's the part there that we are going to say to ourselves in that laminar flow section, that's my little tiny 3,600 cubic feet per acre that I'm going to capture. But that's not the whole pond. That's just a little chunk of it. So with that in mind, I started talking about this little, if you notice, a rectangular shape. I had to do a rectangular shape, something to make sure the math would come out approximate. And then we put fudge factors in for the final picture you'll see in a minute. But I started saying, let's take a look. Here I have, and you notice we got metric and imperial units in here, so 10.6 cubic feet per second coming down into here. And the bottom one is 3.5 coming in there based upon this equation where the surface area is equal to the discharge going out of the system. There's the key word I'm looking for, flood flow conditions, divided by how fast the particle falls through water, terminal velocity. Well, just to save a little bit of headaches here for you, if you were to take that point right there at capturing 0.01 millimeter size particle, you would need a pond that have a surface area of more than an acre in size. Now, a lot of highways have that size, don't they? Not. So you start saying, well, what happens if I take that 0.01 and go to 0.02 after I draw that line there? Go over to here, the pond is 74% smaller going from a 0.01 to a 0.02 as being my design parameter. Well, that's not bad. Look what happened. From 46,000 to almost 12,000. Because I increased the diameter of what I'm capturing. So the key word in here, what size particle do you capture? By the way, on publications with EPA, that seems to be the number that they centered in on, based actually on the Office of Surface Mining. But look what happens when we go to 0.03, 88%. Look what's happening to the size of that surface area. The pond's huge for small pieces, gets bigger, bigger, bigger. The pond gets smaller and smaller. And you can go through down onto here to finally, if you're trying to capture 0.05, look how small that sucker is. So, translation, know the size particle you're trying to capture. Don't just stay with the volume being captured. Know the size particle you're going to capture. This one is going to be the sands and large size particles that are coming in there. These are the clays that can cause an awful lot of problems to the gills of fish and everything. So these are the things that I want you to be aware of and be cognizant of. Here's a whole bunch of equations, and we'll quiz you at the end of the day about the test when it comes. Oh, didn't I tell you about the test that's coming up on this? No, I didn't. I'm sorry. All right. These are just a whole series of equations that work onto here. This is the one I want to concentrate on. Minimum containment volume. This is that little chunk in the middle that we're trying to find. What is it? Well, determining a minimum containment volume, this is what EPA says. This is what Hawaii has, 3,600 cubic feet per acre. Now, the question I'm going to ask now is a nasty, nasty question. Why? Why do you stay with that number? Is it the correct number? Is it too small? Is it too large? Is it realistic? We'll find what out as we go through it here a little bit. It came from EPA, actually it came from Maryland, but EPA put it in publication in here. This is a statement they made in that publication. 3 inches of rainfall represents a 2-year, 24-hour storm event in the United States. Right. Let's see what that looks like. Blue is the 3-inch. That's greater than 3 inches. That's less than 3 inches. On the mainland, most of the land has less than 3 inches. Hawaii, Oahu right here. I don't see any blue lines anyplace, do you? Over in Hawaii, I notice Hilo is not over in that category for some reason. So, that's not a very good statement. It's not a valid statement. But they made another statement. 3 inches of rainfall will result in 1 inch of runoff and 2 inches of infiltration. And by the way, that particular value, this is how they got that number for 250 cubic meters, because 25 millimeters is about 1 inch. And this is what we did for 3,600. It actually comes out to be 3,630 cubic feet per acre. We rounded off to 3,600. Now you know how to have calculated if you indeed ever needed to. It only works though for sandy soils. Does not work for clay soils. It's just the opposite of clay soils. Most of it's 2 inches of runoff for 3 inches of rainfall. So we're stuck there. Then they have this really silly statement. 90% of all rainfall events result in 1 inch of less of rainfall. That is not so far-fetched. Let me show you why. Let's take Honolulu, and then we're going to take Hilo after that. So we're going to have relatively dry. We have about 17 inches of precipitation in Honolulu. That's all the rainfall events from 1996 to 2016, to the beginning of 2016. 20 years of data. And you look at it, and by the way, there's 1, 2, 3, there's 4 of them that exceeded 4 inches of rainfall. Look where most of them are, down here. Matter of fact, look at that number. That's your average rainfall in Honolulu at the airport. 0.184 inches of rainfall. Really? You just told me I have 10 minutes, and I've got about 20 minutes to go here. So well, I better hurry up then. Potential runoff events for Honolulu precipitation. If you look at the graphs, a little bit different now. And if you do a pie chart on them, you'll see that 79% of the runoff events are a ½ inch or smaller in size. 6.5 and so forth on down the line. Sorry about that. And that's 6.5 up here. There's your 2-year, 24-hour runoff event for Honolulu. Now, take Hilo. Hilo itself, a couple of little spots there. They had a little bit of rainstorm the other day or two, didn't they? And when you go through there, down here, that's where the runoff for about night, but that's the runoff of a ½ inch of runoff occurring. Here's 1 inch, and then here's 1.5, and I stopped with that one on that particular grave. I made those curves, and it was interesting when you plug this all in here, 82% of the runoff in Hilo is a 1/2 inch or less. Kind of interesting little things in there. There's the 2-year, 24-hour runoff. So we take 4 different climatic regimes. Here's Phoenix, Arizona. Here's Denver, Colorado. Here's Atlanta, Georgia. And here's Hilo. Look at the shape. Every single one of them, the majority of runoff is a 1/2 inch or less. Kind of interesting. So we'd say some suggestions that I've gone through, and I've looked at Malaysia, a couple other places. There's my suggestions that we think about what we do for these different climatic regimes. In the arid, semi-arid, let's take 1,800, don't do 3,600, that's too much. In your temperate or humid conditions, that's where 3,600 comes into here. Honolulu is in a tropical climate. I'm recommending that you kick that up to 5,450 cubic feet per acre because you have a lot more storms that come in there. They are a little bit heavier and so forth on down the line. So there are just different ways of looking at this thing. Every spot's different. Go on the east side of Honolulu, of Oahu, totally different regime than what you see here. 3,600 isn't going to come close to help do anything over there. So we go through in there, we have those little equations that we have going on here. This is all now thinking about what we're doing for this containment system in here, but we've got the rest of the pond that we have to worry about. And we take care of that by what I call the adjustment factors. Some people call it fudge factors. Some people call them safety factors. Basically, you have to start using your expertise on how you figure out what some constants are going to be to fill in the stuff beyond the actual laminar flow sections. There's a whole bunch of goodies in here to deal with. About your outlet structures. On your outlet structures, maybe you like gabions. They work for holding water back, which is good, but it also lets a lot of water go through, which can be bad. Riser pipes, you probably have a lot of details on riser pipes. The trouble with riser pipes is that they don't work as good as skimmers. These still transmit a lot of sediment off the site. These transmit a lot less sediment off the site. And why? Because they float on top of the water about anywhere from 3 to 6 inches, and they take the water where the sediment's the smallest. They're reusable. They're very handy to use. So if you happen to have a single chamber pond, like I'm trying to illustrate there, and you have about 8.3 cubic feet a second going through it, plan on it going to 8.3 cubic feet per second leaving. And your whole design can be set up with these equations that I threw into there, where you can get the length and you get the width based upon flood flow conditions, not based upon the minimum amount of sediment or runoff to capture. A lot different. So the pond's bigger than what you would think it would normally be. Just a little comparison onto here. Just a schematic, that would say that represents about 16,000 cubic feet of storage for this pond. That would be 235. The containment system itself, if you were to drain it out at, say, 0.35 cubic feet per second, it would take you 41 hours to drain that pond out, which is good. Except if you're in construction business, you want to have that be 4 hours, not 41 hours. Understandable. But water quality-wise, we can't do it. Can we answer this question? The answer on this is yes, we can make them smaller. Keep the land disturbance smaller. Keep the upstream lands in stabilized condition. Eddie talked about that one a lot. Deepen that pond, that helps. Install internal baffles, such as what we have here. They can be impervious or they can be pervious, but is the pond big enough for the volume that you're anticipating? You've got to plan it out. Make sure pond maintenance is a priority. And here's the one that's a big one. I know of 2 states that cannot use flocculants. One's Colorado. I'd like to take a guess where the other one is. You're living in it today. why you can't do it yet. So, but think about it. If we can use flocculants to remove sediment from drinking waters, why can't we use flocculants to remove sediment from runoff waters? I'm going to leave that question to you and all the politicians. But it's a good question to ask. And this is just trying to illustrate, this is the water that came as simulating and designed inflow waters, treated with a polymer, coming down over to here, coming down over to here. It took 96 hours for that water to settle out. Now it only took 44 seconds. They have their use. But there's a chemical. We got to study it. We got to know what's there. We got to know the limitations. We got to know when we don't use it. That's probably more important than when we use it. So we go into there, but look what happens. Remember, this is the first size without any flocculant? It went from 16,000 down to 5,000 in size. Same thing over to here. It took 41 hours. You can drain it out in now 15 hours, and maybe quicker if you have the right treatment in there. So basically, as you go through in this, as we summarize it, getting close, aren't I? Summarize these things, we don't have any control, but we got to design for is discharges out of the system. And that's fine and dandy, but remember, the higher the discharge, the lower the efficiency of our pond. The lower the discharge, the higher the efficiency. That's why you need the skimmer. That's the low way of doing it. And internal flow velocities, you gotta have handles on that, which we do in our other class. Gotta know what size particle you're trying to capture. And think about the pond itself. That is a design of an efficient pond because there's a long flow, short width. Length-width ratio, at least 3 to 1. Not 2 to 1 just doesn't cut it, I'm sorry. Surface areas depends on the size that we have in the pond itself. How far does the particle fall? The containment volume. And be sure that start thinking about this. I'm just throwing it out, start thinking about it. We've got to start thinking other ways. Eddie hit the nail on the head. Think about out of the box. Think about what can be used to make our systems work better. But know the limitations. The biggest problem people have, they put something on without knowing that it could be damage to the environment. So know the limitations. If you have all of that, you can go a long way to having an effective and efficient said pond. Thank you. I made it right on the fight, Mark.